My name is Rohan Jadhav, and I'm the TA for Polymer Reaction Engineering 2023. So I'll be showing you some sample problems for solving assignments 1 and 2. First, we will begin with the normal standard question for what does polymers mean? The word polymer, what does it mean? Uh, a pictorial representation is given here. As the definition says, MERS, polymers is formed with two words, poly and MERS. MERS meaning many parts, and poly meaning the monomers arranged together. So you can see here, these are two different kinds of polymers. As you can see, small, these spherical beads, they are the monomers which are arranged in a chain fashion, forming the polymer chain. And these polymer chains will have different mechanical properties and chemical properties depending on what way they are joined and what kind of monomers are joined on them. Like monomers can have functional groups uh, that gives them their own respective special properties. Here you can see in the example as there is cross-linking bond forming, which gives it a rigidity. This polymer species has a certain rigidity. Here there are no cross-linking forming, so they are just an entangled mass. The next question is what are these monomers? Now, these monomers themselves are the smallest molecule in the polymer chain. Here you can see monomers, small monomers forming a large molecular chain. The largest unit in the polymer, the molecular weight of each repeating unit should be less than 10 units. This is just a condition placed on what should be the weight of a monomer. But this is not a hard and fast rule for any polymer. So as you can see, the correct answer would be the second. You can see here like a monomer can be of any size. Here you can see a cross-linked phenolic resin has been shown where the monomer itself is a benzene ring attached with an OH group. Now this monomer is then formed into this cross-linked polymer, as you can see here, which has branching, cross-linking, and terminal monosubstituted groups, as you can see. This itself provides a rigidity to the polymer and its different properties. Now, you might have seen in your videos that reactive species R star are shown in radical chain polymerization reaction as this. So here is an example of how this radical reactive species looks like R double O R. You can see 2R O star, which initiate the chemical reaction and propagate the chemical reaction. As you can see here, and the termination also occurs in a single. The polymers which melt the first time when they are heated and during the first heating, the polymer is pure, and after that it does not melt on reheating and degrades after that. What is it called? So this is the basic of the uh, polymer reaction engineering. To know what are the inherent properties of the polymer. You can see here that first we have thermosetting polymers, then thermoplastic, elastomers, and fibers. These four are different classes of polymers, but the one which is required here is which is heated first, and during the first heating, the polymer is cured. This will be your thermosetting polymer because thermosetting polymers, as shown in this diagram right here, when they are cured, they form cross-link. Because of this, the individual polymer chains they join together because of this process. Okay, and this cross-link itself, what it does is it provides the rigidity to the polymer because of which it cannot move. Now, a normal polymer, when you provide it heat, what happens is the polymer chains can slip past each other and it will melt, form a viscous melt at high temperature. But when cross-link bonds are formed, what it does is it provides a rigidity to the polymer, because of which this polymer will not move at all at high temperatures and it maintains its strength. But as the heat increases, this polymer will collapse and it will degrade. The polymer will start losing its property and it will form ash because of the high heat. Since it cannot dissipate that heat anywhere else, it will degrade. And that's why the for this question, the answer would be the thermosetting point. Next, we have which of the following can be used for impact-resistant materials and are also used as thermoplastics, elastomers, compatibilizers, or emulsifiers to create stable blends or alloys. Here, yeah, you can see that alternating polymers, statistical gradient, and graph. If you have done your lecture properly, you would know that grafting is a technique which we use to make give better properties to a polymer. Now, what it does is impact resistant materials form from grafting polymerization. What it does is basically grafting increases a polymer's force dissipation capacities. Now, if a polymer is able to better dissipate force, what it will do is it will increase its impact resistance, and that is exactly what grafting polymerization does. Now, broadly, polymerization can be categorized into two categories: step or growth condensation polymerization and chain growth or addition polymerization. The classification based, okay, okay, yeah, yeah, go behind. Yeah, right, okay, yes. I'll explain again. Elastomers, elastomers are elastomers are also polymers, but this is different. Neoprene, rubber, isoprene. These are elastomers. They have they can expand a lot. If you if you tie them at one end and then stretch it at the other, they will it's like an elastic. That's how the name elastomers comes into picture. They are very extremely flexible. But since they are elastomers, they cannot handle heat very easily and they melt very quickly. If you take your rubber itself, if you just put it under flame, you can see that it starts changing and deforming very quickly. That's why elastomers cannot handle any heat. And uh, fiber here is just fiber. Fiber can be a part of a composite. Composite made up of polymer fibers. That is nothing but your polymer composite. Uh, Polymer composite is nothing but the reinforcement and resin. The resin being your thermosetting or thermoplastic, and the fiber itself being any polymeric fiber, such as you have Kevlar or you have carbon fiber, which forms composite. Which of the following have a higher melting point? So you can see here there are three options. Okay, crosslink, branch, and lean. So you can see that linear polymers, right? Linear polymers, what happens with linear polymers is that if you provide them heat, the only thing resisting that heat is the entanglement of the individual polymer chains. Since linear chains are long enough, they get entangled very easily. Because of that, what happens is uh, they can uh, they are able to resist heating, and because of that, its melting point is slightly high, only slightly high. Because if you provide any more heat, the chains gain enough energy to slide past one another, and then they melt. Next comes branch polymers. Branch polymers are not as packed as linear polymers. So because of that, because of the branching, they are not able to uh, form any entanglements. And because of this, their melting point is even lower than linear polymers. Now next comes the cross-linked polymers. What happens with cross-linked polymers is cross-linked polymers have cross-linking between individual chains. Again, Again, we come back to the same concept that forming strong cross-link bonds between individual polymer chains makes the entire polymer rigid, because of which the individual movement of the polymer chains becomes hard, and because of this, it is able to withstand that much heat. So the answer to that question would be that cross-link polymers have higher melting. Yes, yes, cross-link polymers have higher melting. Because branch polymers, what happens with branch polymers is that they are not able to, pack themselves into a uh, single proper long chain. Since branching is allowed, individual polymer chains, right? Different polymer chains, they're able to, they don't interact with each other as much, and because of the branching, there is no structural crystallinity to the polymer itself. Which type of material is generally used as an electrical insulating material? Now, as discussed before, thermosetting polymers, we have seen that can withstand very high temperatures, and thermoplastics, they lose their properties under high temperatures. Then we have elastomers and fiber. Most of the time you would have seen that all around you, all the electrical appliances, they usually in the sense like mainly, they use thermosetting polymers as their insulating material because since you know that flow of current generates a lot of heat and that heat can only be offset by a thermosetting plastic because uh, it is made for resisting that kind of temperature. That's why all the electrical insulation is done with thermosetting plastic. One good example would be that all the switchboards which you see around you, right? Yeah, all the switchboards. Those switchboards are made up of melamine or bakelite. Melamine or bakelite. Why? Because these are thermosetting, and since they are thermosetting, uh, they can withstand heat, and that's why any kind of electrical fire, in that case, those materials are good as they don't melt away. Or else, that much high electrical heat, if it's applied to a thermoplastic, it would melt and it can cause a hazard. Since we're talking about cross-linking itself, uh, some of the products which form cross-linked polymers are phenol formaldehyde or bakelite. They are the same thing. And urea formaldehyde. You can see here a reaction scheme is given for urea formaldehyde. Sorry? Okay, yeah. So what happens with step growth polymerization and condensation polymerization? In step growth polymerization, individual units are repeated and that forms through by radical polymerization, radical chain polymerization, which creates your uh, step growth polymerization process. And next is your condensation polymerization. One good example is right here, as you can see, the adipic acid and hexanediamine, when they combine, you can see here this NH2 group. This will lose one hydrogen, and this adipic acid will lose one of its OH. This will give you a condensate of water right here, as you can see, and then a nylon species. Nylon 6,6 will be there. Since water itself has condensed out of it, this is your uh, condensation polymer. Yeah. Okay, I suggest you finish the assignments 1 and 2, and then uh, your deadline. Uh, Once that is done, we can discuss more further about the upcoming concepts. Yeah, that will be taught in the next class.